Morning, everybody. My name is Kirsten Perry. I'm a data scientist in the PV Reliability and System Performance Group at NREL, and today I am presenting on PVAnalytics, which is a Python package for automated processing of solar time series data. I'd like to thank all of my co-authors who contributed significantly to this package thus far. Will Vining, Kevin Anderson, Matt Muller, and Cliff Hansen, who just presented. Off to the side here, before I even start, we just released our new PVAnalytics version V0.1.2, and we've got our documentation here on GitHub for PVAnalytics, which is under the PVlib umbrella in terms of being in the PVlib org. So before getting into things, I want to give a brief outline of the contents of this presentation. First, I'm going to provide a little bit of background on PVAnalytics, go over some of our package features, how we're validating the algorithms within the package, our documentation updates, as well as our automated testing protocols, community growth, and then what's next for PVAnalytics in terms of version 0.1.3 and beyond. So getting into it, background on PVAnalytics. As most of us know already, ground-based solar time series data can vary significantly in its quality or lack critical metadata. Several key solar metrics are used that require data cleaning and filtering before they can actually be calculated. This includes performance loss rate, power production forecasting, as well as soiling loss calculations. PVAnalytics seeks to tap into this vein by automating the processing of solar time series data, including QA, QC. So this is pretty much, this package comes in before we actually do the analysis. It consists of a few key components: data quality control and filtering, identifying system characteristics, which can include stuff such as mounting configuration, azimuth, and tilt, as well as feature identification, such as detecting clipping in time series, day-night masking in time series, as well as clear sky detection. And you can see here down at the bottom, we have a read the docs for PVAnalytics, so feel free to check it out. Continuing in on our background. So there's a few key design principles behind the package itself. First of all, we wanted something that was open source, so freely available to the public, tested, documented, and reusable. And by reusable, I mean you can run a function over and over again on a set of data and you're going to get the exact same results. We wanted something that was independent of a particular analysis workflow. So we wanted it to be, our functions in PVAnalytics to be more plug and play. So you can decide what functions you want to particularly implement on your time series and go from there. Next, we want our PVAnalytics to be a collection point for code which implements published algorithms. I'm going to talk a little bit more about the publishing part during our algorithm validation slide, but we want our code to be robust and also rigorously benchmarked. Thus far, PVAnalytics has been a collaboration between Sandia and NREL. However, we really want this to be a community-driven package. And it started as a Duramat project back in 2020. For those of you who don't know what Duramat is, it is a DOE-led consortium for PV module reliability and durability. And the functions currently within the package come from two main places: Solar Forecast Arbiter, as well as the QA process from the NREL PV Fleets Initiative. I actually work in PV Fleets on the QA side, which is how I got involved in this project. I'm going to do a quick plug for Fleets in here since I work on it. So Fleets right now is a large-scale data aggregation effort for solar time series data from sites across the United States, where we calculate the degradation for the entire United States fleet. Right now, we have about 2,700 systems sitting in the database, our cloud database, and over 30 billion rows of time series data. So without further ado, let's talk a little bit about the package features. Starting basic here, we've got basic time series filtering routines in here. We have an outlier detection and filtering module. It includes 3 different filters, including a handful, a z-score, and a 2-key filters with tunable parameters. So you can pass whatever parameter you want. If you want a z-score of 2 or a z-score of 3 to detect an outlier, you can do that. You can see here at the bottom left, the Hample filter in action, detecting outliers in orange. Next up, we have a stale data detection algorithm. So this essentially looks for consecutive repeating data values within a time series. and marks them. And you can see this algorithm in action in the bottom middle figure, where still data periods are reflected in orange. And then next, we have an interpolated data detection algorithm. So this essentially is handling situations where, let's say, your data goes out and it just interpolates, your data system interpolates for that whole blank period. You might not want that data in there. So we've got a function for detecting those interpolated data periods, and then you can mask it and filter it out. Next up, going into some of our more advanced time series filtering routines, we have a function for detecting missing data periods and essentially filtering out days with large data gaps. So we do this via a completeness score. So essentially we look at each day of data, find what the data holes are in it, and if there is too much data missing, more or less, there's a settable parameter where that period gets filtered out. You can see this in action here on the bottom left of this slide with incomplete days filtered out in orange. Next up, we have a data shift detection and filtering algorithm. So I worked on this earlier this year and presented it at PVSC. So essentially, a lot of the time series data can have massive data shifts or capacity changes happening. A lot of the time it occurs because of hardware configuration issues. So let's say somebody decides to change an AC power stream to an AC energy stream in their system. It changes by a factor of 4x. They don't account for it. We've seen it in time series data. We want to be able to detect those massive shifts and look at those periods within the time series separately, or even filter out the really erroneous periods. So this algorithm uses change point detection to find these massive abrupt capacity changes. And you can see this algorithm here in action. It performs a data shift calculation here automatically. It's unsupervised ML, where the first segment is in blue and the second segment is in orange. Next up, we have feature detection capabilities in PVAnalytics. So we have a day-night masking algorithm. It is a logic-based routine for masking day periods from night periods. First of all, this may not seem like the most useful algorithm. However, it really plays into the fact where if you're trying to detect time shifts in your daily data or daylight savings time, you can actually correlate your sunrise and sunset values over time to that daylight savings time. So after a DST change, more or less, your data, your sunrise and your sunset are going to shift by an hour. And that's something we're working on adding in and validating our DST algorithms in here now. I'll talk a little bit about it later. Next up, we have a clipping detection and filtering algorithm. For those unfamiliar with clipping, inverter clipping, power inverter clipping happens when the inverter is overloaded. Essentially, it manifests as a flat line at the top of your daily production profile for your AC power profile. And this more or less data, we have this function detect this data in here, those flat line periods. Here's the function in action here, up here where clipping periods are labeled in orange. We did a presentation on it earlier, PVSC 2021 last year, so you can check that out. And last but not least, we have a shading detection algorithm. So this algorithm uses a morphological image processing method to identify shadows in GHI data. This is based on a method actually that Cliff contributed to, who just presented, and we've got a citation there for it as well. Next up, we have Irradiance checks within the PVAnalytics package. So we have data quality checks for Irradiance. A lot of these are focused on QCRAD criteria. So we check the consistency and the physical limits of our GHI, DNI, and DHI streams for our ground-based data. You can see the consistency QCRAD algorithm at work here at the bottom left of this slide. Where consistent periods are masked in blue. We also have a clear sky period filter in there. And I guess the I guess the image here has the clear sky periods in black and the non-clear sky periods in blue. A little hard to see. Hopefully you guys have zoom up in here, but that uses the Reno clear sky method to detect these periods throughout the day, which are clear sky. Next up, we have a clear sky day filtering algorithm. So this even takes that period algorithm further and just tries to find days that are very close to clear sky days. So you can only filter out and get clear sky days only. What we do here is compare GHI sensor-based data to clear sky data. And then we filter where GHI is within a daily insolation limit. And you can see this algorithm in action with clear sky days outlined in green at the bottom of this slide. Next up, something very near and dear to my heart is system characteristic identification. As I work on the Fleets Initiative, sometimes we get data from our partners where the metadata may not be correct or it may be entirely missing. So this is something that is a big research topic for me. In here is identifying mounting configuration, azimuth, and tilt just using time series data. Here we have an example for mounting configuration up here, where we use a time series to detect whether or not the stream is associated with a fixed tilt or a single axis tracking value. This graphic right here shows the daily production profile for an AC power stream. As you can see, it fits a quartic kind of equation in there, and quartic equations are highly associated with single axis tracking systems. So you can identify this as a single axis tracker. The black line, which is a quadratic, associates with a fixed tilt system. Next up, we have azimuth and tilt. This is definitely a work in progress right now. This is actually what I'm working on currently. We have multiple methods in the package right now that calculate azimuth and tilt, and we're in the process of benchmarking those using several different systems with azimuth and tilt values and time series, just so we can quantify how well these algorithms work. Next up, we have algorithm validation. So I just presented a ton of functions to you, but they don't mean a whole lot without some kind of benchmarking aspect to them. So that's something that I've been working a lot with my colleagues to validate these algorithms using a lot of anonymized PV fleets data. So I'm really trying to answer the question of how well does each algorithm perform for its associated problem, using quantifiable metrics such as accuracy and F1 score, because a lot of the functions that I just presented to you technically qualify as classification problems. With my colleague Matt Moeller, we've actually been labeling data sets manually. So, hey, this entry is associated with a clipped point, and this isn't, so on and so forth, for several different systems with a variety of different behavior, and benchmarking how these algorithms perform. We are also releasing approved anonymized versions of these data sets on the Duramat Data Hub so that other people can access it. This is not only just to encourage benchmarking in PVAnalytics, but also to encourage any supervised machine learning work if anybody wants to do that, because these data sets to a large extent don't exist. And on top of that, we've been working on technical documentation and publications for benchmarking each one of these algorithms' performance. Next up, a little bit on our, I guess, documentation for PVAnalytics itself. So we recently released our example gallery in version 0.1.2 last week. And this gallery includes example data from our public NREL PVDAC database that I took off of there. And these new data sets are actually run through each one of the functions, so you can get a step-by-step process on how to run the functions in the package. We have it done for about 80% of the functions. I still got to do the other 20. That's on my to-do list. And then it also includes plots illustrating how each algorithm performs. So you may be asking yourself now, how do I actually apply PVAnalytics to my data? How can it easily be implemented? So I added this slide in last night just to give kind of a rundown on how this applies to you. So let's say you have a CSV containing a whole bunch of data streams, so AC power, radiance, temperature, and you have hopefully time zone localized timestamps in there. You can throw it into one of our example documentations on a read CSV for pandas. You can adapt any of the metadata parameters associated with that documentation. So let's say the lat and longitude coordinate, as well as the data frequency of your data. Is it 5 minute, 1 minute, so on and so forth. You can run your associated example, get those outputs, and then analyze it. So it's pretty easy if you just refer to the example documentation, which is great. Next up, a little bit on our function descriptions. So we kind of modeled off of PVlib for a lot of how we formatted PVAnalytics, because PVlib's the gold standard in here. So we do have a page for each model function, which contains a brief description of the function, as well as input parameters such as the data type, the description, and output parameters with the same values, more or less. A publish reference for the function if it's available. Ideally, eventually we'll have publish documentation for each one of these functions, so in the future. And then any additional notes as needed, and also any links to examples in the gallery that relate to this specific function. Included in our testing suite is automated testing. So whenever we submit a PR, it goes through an automated testing protocol. So we do have comprehensive unit testing for all of our functions. We have virtually 100% test coverage. I think I tested, or I had a look at it earlier this week, and it was like 99.7, which is really good test coverage in there. So all of these functions have been rigorously tested, which is amazing. We use PyTest and coveralls to do this. So very similar to what PVlib does already. Since the package is in its infancy, we don't have any speed benchmarks yet. But eventually, depending on how it grows, we may add speed benchmarking in the future. Now a little bit onto our community growth on GitHub right now. So PVAnalytics obviously has not been around for that long. We've only had, I think, 3 versions released so far. Within those 3 versions, we've had 88 completed pull requests. And we have co-contributions from 6 people. Special shout out to those 6 people right here on our contributors list. This package wouldn't exist without all of them. And since PVAnalytics is so early on, there's a lot of opportunity to really grow this thing by the community, since it's still in its infancy, and turn it into something that the community, the solar community at large, really wants. That being said, you could definitely contribute. There's a few ways you could do this. Obviously, you could submit issues for debugging. You could generate issues for features that you'd like to see in the package. You can add code via our PR process. Other various, ways to do that, like contact us and ask us for particular things in terms of what you'd like to see in the package in the future. And last but not least, a little bit on what's in store for PVAnalytics for version 0.1.3 and beyond. So obviously right now we don't have an expected ETA for our next release because we released our last release literally last week. But we're actively working on new functions and documentation every single day. So we're hoping to add that extra 20% of documentation. So we have, example galleries for every single one of the functions in the package. Some of the future version features that we would like to add would be a daylight savings time and time drift detection algorithm. We've got some code in there right now, but we haven't tested it out yet. Want to make sure that it's rigorous, works for everyone before launching that. And then adding plotting module functionality so that you can easily visualize your data streams as you make changes and stuff like that, and assess whether or not the algorithms worked. That being said, thank you so much for your time today. Obviously, if you have any questions, this is my email. Feel free to talk or contact anybody in the PVAnalytics group, and definitely check it out. Thanks, everyone.